Okay, so today we're going to talk about enthalpy and Hess's law. And as my little caption says, it's about the destination, not the journey. There may be multiple pathways by which a process could happen, but what we concern ourselves with is the energy at the beginning and the energy at the end. So let's talk about energy either being a reactant or a product. So when we write what's called a thermochemical equation, what we have is not only the reactants and the products, but we also indicate what the energy change is. So if it's exothermic, of course, the energy is a loss of heat energy by the system to the surroundings. And so we can write that adjacent to the reaction, much like we did here when you burn methane, heat energy comes out to the tune of 890 kilojoules for every mole of methane. And that's important to note. Whenever we include the heat value, now we're talking about per mole of reactant, which will lead us sometimes to have some funny equations in that this is the only time we can have fractions in our coefficients. Okay? So we can also write it as part of a reaction. So as you see here, I included it, and I included it as a product because the heat energy is coming out. It's produced as a result of the reaction. Okay? If this were an endothermic reaction, it would be on the reactant side. It'd be over on this side, indicating the energy was absorbed as part of the process. It would feel cold to you because you would be the heat source. The heat would be going from you into the system. But in this case, with methane, we're burning it. It's coming out, it's generating heat. So Hess's law. Hess's law is basically says that heat transfer, as I indicated at the beginning, is a state function. Whichever the multiple steps or pathways it could happen, all we care about is the energy at the beginning and the energy at the end. So another way of saying that, all paths have the same energy change, conservation of energy. Or as the chem team quote that I've included here says, the enthalpy of a given chemical reaction is constant, regardless of the reaction is happening in one step or many steps. The energy change doesn't differ depending on which path you take. Why is this useful? If I'm trying to find the enthalpy change of a reaction that I don't know what the heat change is directly, or it's difficult to measure it experimentally, but I have other reactions that have in them bits and pieces of the unknown one, and I know their enthalpies, I can make them add up in such a way that I can also add their heat changes, and then I'll know what the actual result of the unknown reaction is in terms of energy change. Okay, we're going to go through an example of this on another slide. So if a chemical equation can be written as the sum of several other reactions, the enthalpy change of the unknown, or the first one, is equal to the sum of all the other changes that add up to that reaction. So let's look at what this means. As I said, an example. So let's make ethine, all right, C2H2, two carbons held together by triple bonds, each of them having a hydrogen attached to them. Now, if the enthalpy of this reaction is unknown, how could we figure it out? Well, look at that I have three other reactions here. The combustion of ethine, which of course would be exothermic. The formation of carbon dioxide, so basically the burning of coal or pure carbon, also exothermic. And the formation of water from hydrogen gas and oxygen gas. And you notice in two of those equations, we have, again, that sort of funny fractional values here, because the enthalpy change is per mole ethine, per mole carbon, per mole hydrogen. Okay? Each of these three reactions have bits and pieces of the first reaction up above. And so if we can make each of these look as much as possible like that one, so that when we add the three of them up, reactants in one reaction that are products in another cancel out, and what we're left with is carbon and hydrogen producing ethyne. Whatever we do to change these reactions, we do them to the enthalpy changes, and when we add up the enthalpy changes, we'll know what our unknown enthalpy change is. Let me take you through. Okay, the three equations, as I said, are going to be rearranged. And so here's the solution. So there's the equation again that I'm trying to solve for. So let's go through each of the changes. So the first one has the ethyne on the reactant side, but we're trying to figure out what the energy is to make it. And so as a result, this is backwards. So we have to reverse the reaction. If we reverse the reaction, guess what happens to the enthalpy change? It's the same quantity, but it's going in the different direction. Instead of leaving the reaction, it's going into the reaction. So I have to change the sign. In terms of the molar coefficient, I have one ethyne, I have one ethyne. So I don't have to do anything else. I have to just reverse the reaction, which changes the sign. In the second one, I have carbon and oxygen giving me carbon dioxide. The carbon is the piece that's in the reaction that I'm trying to solve for, but there's two of them. And so I have to double this to make it match. So by doubling this, I have to double the delta H value, the enthalpy of the reaction. For the last one, the hydrogen is where it should be. So I don't have to do anything with that. And in terms of molar quantity, it's also matches. So I just leave this one alone. Now when I do that, if I add these three reactions up the way they are, the gray ones. So let's see. Carbon dioxide is a reactant here, but in this other reaction, it's a product. Water is a reactant, but then it's also a product. The oxygens, two whole oxygens would be 4 halves, plus another half makes 5 halves. And so that cancels out the 5 halves over here. And so what am I left with? I'm left with carbons and hydrogens, giving me my product. So if I've lined it up, so the only things left are the reactants I wanted and the products I wanted from the one I don't know the enthalpy change of. Whatever I had to do to those other equations, so when they add up to that equation, I add up the enthalpies. And lo and behold, I find that this reaction is going to cost the surroundings 226.7 kilojoules for every mole of the ethyne that I'm going to make. Now, that reaction, think about it. We started with pure carbon and pure hydrogen, and we made a molecular compound, ethyne. Whenever we start with pure elements and produce a product, what we have done is figured out the enthalpy change of that reaction. And we call that the standard heat of formation, the energy it takes to build a molecule or to build an ionic compound out of its pure elements in their standard state. So standard state, 25 degrees Celsius or 298 Kelvin, room temperature basically. If it's a liquid, it's pure. If it's a solution, it's at 1 molar. If it's a gas, it's also pure. And as a gas, it's at 1 atmosphere of pressure. Those are considered standard conditions or standard state conditions. So if we take every element in its standard state, so metals would be solids under those conditions. Most non-metals, some are solids, some are gases. Bromine's a liquid. And as we put them together to build compounds, the energy change it takes that either goes into or comes out of producing those is the standard heat of formation. So in the last slide that we did, when we worked out, we actually worked out mathematically from some known values the heat of formation for ethyne. Okay, so every pure element has a heat of formation of 0. If it's pure and it's in its simplest form, there's nothing to build it out of, so there's no energy change. Okay, when we know those delta HF values, those heats of formation, those can also be used as a way to calculate the enthalpy of any reaction. So most of the common substances are table values. There's a table value. Okay, so this is just a sample that I found from a wiki page that gives you the overview of some different substances and their heats of formation. Do notice, for example, water as a liquid or water as a gas vapor, they have different delta H values. This is why the state of the matter, the state of the compound is important, because the heat of formation can vary based on whether we're making a liquid or a gas. So we're going to talk about using these heats of formation values to calculate the enthalpy change of any reaction. And we call this equation affectionately Big Mama. And Big Mama is going to change forms from when we're talking about enthalpy now, and later we're going to talk about entropy, and we'll even talk about free energy, and they all play by the same rules. The formation values for each substance involved will lead us to calculate what happens just during the reaction. So it's an application of Hess's law. So the sum of all the formation of the products minus the sum of all the formation of the reactants will give us the reaction. So in other words, for any reaction, the energy change is the sum of, that's what that Greek letter epsilon stands for. It's the difference between the energy it costs to build the products from scratch and the energy it takes to build the reactants from scratch. Any differential energy from building them from pure elements is what's going on in the reaction itself. Again, let's look at an example. So, back to burning methane. Methane gas, when we burn it in oxygen, gives us carbon dioxide and water. It's a combustion reaction. So, if I go back to the table that I had 2 slides ago, there were values for methane, for oxygen, for carbon dioxide, and water. Now, the carbon dioxide has a value, this is the water. The water has a value of 242 kilojoules for every mole of water, and in this reaction we have 2 moles. The carbon dioxide table value is negative 394, and there's only 1 mole of that. So there's the sum of all of the product energy to build the products from scratch, and then in this other set of brackets we have the energy it takes to build methane basically from scratch, because oxygen is a pure element in its standard state, so its delta HF is 0. And so the difference between the energy it takes to make methane from carbon and hydrogen and the energy it takes to make carbon dioxide from carbon and oxygen and hydrogen, 2 moles of water, from hydrogen and oxygen, the difference between those is 803 kilojoules per mole. So for every mole of methane, we get quite a bit of energy out, which is why natural gas is a good energy source. And with this, hopefully you see now how you can apply all of this idea of Hess's law to calculating out the enthalpy change of any reaction. Let me give some credit where credit is due since it's been asked for by my AP students. And I hope you enjoyed this installment of thermochemistry.